In section 4.3, we're going to talk about exponential functions. So what are exponential functions? Exponential functions are functions of the form f of x equals c times a to the x, where c is a non-zero constant, meaning that c just can't be 0 because otherwise we'd just have f of x equals 0, which is just the y-axis. So c is a constant, it's a number. A is the base of our exponential function. A is also positive, a real number, and it cannot be 1 because otherwise we'd just have, another constant function because 1 to any power is just 1. So we would end up with just f of x equals c times 1, which is just a constant or a constant function, which is why we have to put yet another disclaimer on what a cannot be, what c cannot be, just so we don't end up with the same functions that we've always had. The initial value is f of 0 equals c. That means where does it start? The other name for initial value here is also going to be our y-intercept because it's where x is 0. So this is also our y-intercept. What we also know about e is that e is just a number. It is 2.718281828. You can see it in your calculator. If you want to put it in your calculator, you can find this by hitting second and then the divide button will get you the value of e. So let's do that. Let's evaluate in your calculator a couple of different expressions. The first one is e to the 0.635. So the way you're going to put this into your calculator is you are going to hit second and then the natural log button. It may be capitalized. If you have an older calculator, it will look like ln lowercase. If you have a new 84 CE. They are in lowercase, but the older 84 Silver Plus editions and things are all uppercase. So it would just be second, and then the natural log button, whether it looks like a capital LN or a little ln. So when we do that here, we will get e to the 0.635, or it will show e caret, and in parentheses you put 0.635. And then just hit enter. And once you hit enter, you find out that this is approximately 1.887. If you go into your calculator, you should be able to find this. If you have trouble getting this, just let me know, and we can also look at it in class together. Let's try another one. 1 plus 0.03 raised to the 6th here. And you would put it in your calculator exactly as it's given. Put it in parentheses, 1 plus 0.03, close parenthesis, caret button, 6. So we would end up here, if you plug it into your calculator, you end up with 1.194. And again, if you are having any trouble getting any of these values, just ask me about it on Wednesday. The last one is a little more complicated, and we'll see this one coming back more so in the final section of Unit 4 when we start talking about exponential growth and decay. But this one says I have 523 times e to the negative 0.2948 times 6.5. If you're on a newer 84, not even a CE, even if you're on the Silver Plus, you should be able to put it in exactly as it's shown. If you are on an 83, you will need to put in 523 times, right, e, and then caret, and in parentheses, negative 0.2948. And instead of another set of parentheses, just do times 6.5. Okay, and then close it. And if we did this, we find out that we end up with 76.967. So make sure you practice evaluating decimals with your calculator so you'll feel really comfortable about this when we get to that section. We're going to go ahead and talk about graphing exponential functions, and we're going to pull back in some of the transformations and things that we learned in Unit 3 as well. So let's talk about properties of exponential functions. Well, exponential functions of the form f of x equals a to the x, where a is bigger than 1, okay, a is bigger than 1, are going to have a domain that is a set of all real numbers, or negative infinity to infinity, a range that goes from 0 to infinity, and no x-intercepts. So that's a little different than other functions we've looked at. And that's because if you think about, let's say, 3 to the x, there is no value, real numbered value you can put in for x that would cause 3 to a number to either be 0 or to be negative. Theoretically, if you could plug in infinity, you could have something interesting happen, or negative infinity, something really interesting could happen, but we're talking about a finite real number. And there is no real number we could plug in that would cause this function to equal 0 or ever to be negative. Even infinity and negative infinity cannot help us make it negative. So what that means is we have this imaginary line here at y equals 0 that we call an asymptote. An asymptote is an imaginary line that our graph can neither cross nor touch. And we notice that our graph here approaches this line closely as it goes toward negative infinity. On your graphing calculator, it will actually make it look like it's on the x-axis. It's not if you zoom in, but if you try to graph this on your graphing calculator, it will make it look like it's on the x-axis. It is not on it. It just gets infinitely close to it, okay? Never actually reaches it. So what we do notice about this is as we move from left to right, from lower numbers, lesser numbers, to higher numbers, we see that our graph is always increasing. We can see that it has 3 distinct points here. -1, 1 over a, which I have explained down here as a reminder. X to a negative n is the same as 1 over x to the n. So -1 would be a to the -1. And if I have a to the -1, right, then that's the same as 1 over a to the 1, which is 1 over a. So we have that point. We have 0, 1, because a to the 0 power is 1, because anything to the 0 is 1, except for 0 to the 0. And then the third point is 1a. That's because we're taking a to the power of 1, which will always be a. We notice it doesn't have any corners, it doesn't have any gaps. This is a graph that we would call smooth and continuous. Let's look at the graph of f of x equals 2 to the x. Well, we know a few things from the last slide. We know its domain, we know its range. So let's maybe think about those. Let's talk about our domain and our range first. Let's see. Our domain should be negative infinity to infinity. Our range should be 0 to infinity. We should have a horizontal asymptote at y equals 0. And we should see an increasing function. All of these should be true. And then we should also see y-intercept at 0, 1. So we can put that on our graph. We can also put on our graph our horizontal intercept here at 0. Just going to put it in as a dotted line here. And so that's our y equals 0. That is our horizontal asymptote. So we know that's there, and we know we're going through the point 0, 1, which we can label at 0, 1. Okay? Well, let's figure out a few other points. So if we put some x and 2 of x on the line, or 2 to the x on the line, well, let's try maybe -2, -1, 0, which we already know, 1 and 2, maybe even 3. So 2 to the -2, remember, x to the negative n is 1 over x to the n. This is 1 over 2 squared, which is 1/4. So at -2, we have 1/4. Okay, and let's see at -1. 2 to the negative 1 is 1 over 2. That's 1/2. That is our 1 over a. So we get negative 1 comma 1 over a. That is negative 1, 1 over 2. Right? Negative 1, 1 over 2. We already know about 0, 1. Well, that's because this is 2 to the 0, which is 1. At 1, we should get a. In this case, a is 2. Right? A is the base here. A is 2. So let's see here. We get 2 to the 1, which is indeed 2. So we have the point 1, 2. If we plug in 2, we get 2 to the 2, which is 4. So we get 2, 1, 2, 3, 4. And if we were to plug in 3, we would get 2 cubed, which is 8, and it doesn't fit on our graph. What we do know is that we have a few points that were pointed out on the graph on the last slide, which was that at negative 1, we have negative 1, 1 over a, right? At 0, we have 0, 1, and at 1, we have 1a, and those are absolutely true. And if we were to connect our dots here, it would get really close to that line. It would come up through these, and that one would go up and hit 8 and keep on going. And our graph would look like this. Let's make sure we do our 1, 2 here so we can see that one as well. So we can see that we have lots of points that we can put on our graph. And some won't fit unless we change the scale. But we do absolutely see that our domain is indeed negative infinity to infinity. Our range is 0 to infinity. We do have our horizontal asymptote. It is increasing. And we did go through 0, 1. Well, let's explore what might happen if we did instead 2 to the x plus 1. So based on our transformations, our guess is that this is going to be 2 to the x shifted to the right by 1. Well, think back to our transformations. When the plus was with the x, it went the opposite direction. So it's not to the right, it's going to go to the left by 1. So we think that it's the graph of 2 to the x shifted left by 1. So let's draw our number line here, or not our number line, but our sign chart here. Let's just fill in some points. And it's not really a sign chart, but that's okay. We'll fill in our chart. How about that? And let's just plug in some points and see if we end up with the same thing that we think we will. So let's try it. So here's our x. Here is our 2 to the x plus 1. All right, let's look at some values. So let's see here. If we had negative 2 last time, if we go to the left, that would be negative 3. So let's see here. And then we had negative 2, negative 1, 0, and 1. Let's see if we go that far, what happens. So if I look at negative 3, that would be 2 to the negative 3 plus 1 is negative 2, which we know is 1/4. If I put in negative 2, that becomes 2 to the negative 1, which is 1/2. 2 to the negative 1 plus 1 is 2 to the 0, which is 1. 2 to the 0 plus 1 is 2 to the 1, which is 2. And then we get 2 to the 2, which is 4. Now, if I did 2, it would be 2 to the third, which is 8, which would not fit. So let's plug them in. 1, 2, 3, negative 1, 2, 3, and 1/4. Negative 2 and 1/2, negative 1 and 1, 0, 2. There we go, 0, 2. Let's see here, and 1, 4. Well, it looks like it's a very similar graph, if not the same one, but just shifted left by 2. What we haven't put on yet is our asymptote. It hasn't changed any. All we did was shift left. So our asymptote stays in the same place. So that's still y equals 0, our horizontal asymptote. And what do we notice? Our domain is still negative infinity to infinity. Our range is still 0 to infinity. It is still increasing. And we still have a horizontal asymptote at y equals 0. What has changed is our y-intercept now is 0, 2. And did we actually just take 2 to the x and shift it left by 1? We absolutely did. So I would be happy with saying we were correct. And that's because the shift was with the x. So let's see if we build on this same equation and let's have a shift where we're shifting it maybe down by 3. So this is the problem I meant. We're going to take the same graph that we had before, and we're now going to shift it down by 3. So let's see what happens when we do that. So we'll make our points chart again, and let's see what changes. So you're probably thinking through a couple of options right now with things that could have changed, and you're probably right. So let's see. We have our x, and we have our 2 to the x minus 1, and then let's do 2 to the x minus 1 minus 3 and see what happens. Let's just see if there is a difference. And we know there will be, but let's just see if it matches what we think. And I'll write in our guess here in a moment. So let me do that. Our guess is that it is 2 to the x plus 1, right? 2 to the x plus 1 shifted down by 3. Well, let's see here. If we look at the same values, we had negative 3, negative 2, negative 1, 0, and 1. So we said 2 to the x plus 1 was 2 to the negative 2 was 1/4, 1/2, 1, 2, and 4. What I am going to add this time is I'm going to add in a 2 because it will fit. 2 to the 1 is 3. 2 to the third is 8. Okay. But now let's take all of those values and subtract 3. So when we take all of those values and we subtract 3, 1/4 minus 3 sounds a little bit crazy, doesn't it? Well, that's okay. So that would be, if this is 0.25, that would be a negative 2.75, or negative 2 3/4, right? And that would be what, negative 11/4? 1/2 minus 3 is going to be a negative 2.5, or a negative 5/2. 1 minus 3 is going to be a negative 2. 2 minus 3 is a negative 1. 4 minus 3 is a 1. And 8 minus 3 is a 5. So now that one will fit on our graph. So we have negative 3, 1, 2, 3, negative 1, 2.75. We have negative 2, negative 2.5, negative 1, negative 2, 0, negative 1, right? Let's see here. And then we have 1, 1, and 2, 5. 1, 2, 3, 4, 5. So it looks like our horizontal asymptote is also moving, because if we just graphed this part of our graph, it's going this direction. But it looks like this one is starting to hug this line down here, right? Which happens to be y equals negative 1, 2, 3, right? Which kind of makes sense. If we're going to shift down by 3, it means that our horizontal asymptote went from y equals 0, we went down 3, so it'd be y equals negative 3. So if that's the case, our horizontal asymptote has shifted now to y equals negative 3. So things are just a little different on this one. So now we have our domain is still negative infinity to infinity, but our range has changed. Our range doesn't start at 0 anymore, but we shifted it down 3, so it has to start at negative 3. Means we have a horizontal asymptote now at y equals negative 3. Our y-intercept this time is 0, negative 1, because remember we shifted it first to the left and then down by 3. And we still see it increasing. But it definitely follows the same rules for transformations that we saw in Unit 3. The other kind of exponential function we're going to see in this unit is one that has a base of e. Now, we've talked about e before, and e is called the natural number. It occurs in nature just organically and explains a lot of phenomena we see that just occurs without man interfering whatsoever. It's also called Euler's number, and Euler is spelled E-U-L-E-R, which is probably why it's an E. But E is a very important number for us. We're going to see it in several several sections in this unit. So we need to know what E is. We already defined it as it's about 2.71828, right? So let's see what it looks like to graph y equals e to the x. So we're going to have some similar ideas this time. We're still going to have x and we're going to have e to the x. Okay, so we have x and we'll have e to the x. And the other one was x and then e to the x minus 1, which we can probably guess what that transformation looks like. So we've got here and here. And then we're going to draw on a few points here on both of these. Okay. So let's see how we evaluate these functions. So let's start with e to the x. So if I look at e to the x, let's plug in some of those same points that we saw defined earlier. Negative 1, 0, and 1. When I plug in negative 1, I get e to the negative 1, which is about 0.368. Okay, because this is, let me write it out here for you, is 1 over e, which is about 0.368. So negative 1, about there, about a third. At 0, I get e to the 0, which is 1, so 0, 1. And at 1, I get e to the 1, which is e, which is approximately 2.718. 281828. So 1 and 2.7. So our graph is still going to look like this. It's just going to go up a little bit faster. And now we have our horizontal asymptote here. Still at, there we go, still at or y equals 0. So we still have our horizontal asymptote at y equals 0. It's still increasing. It still goes through 0, 1. So it's not all that different than what we've been seeing. So we have, here we have our negative 1, 0.368, 0, 1, right? And 1 and 2.718. So what happens then if we take this graph and we shift it? And we shift it by 1. In the same way that we were shifting before, this one on the second problem here, this one's going to shift right by 1. So everything we see over here, we can just bring over and shift to the right by 1. So now we're at 0.0.368. We're at 1, 1. And we're at 2.7. There we go. 2.78. So now we get the same graph, but now this time it's just shifted to the right by 1. And we'll plug in some points to also go with that, right? We're going to plug in the points to show that they match. So in this case, if we're shifting to the right, we're going to have 0, 1, and 2, not negative 1, 0, and 1. We shifted right by 1. So add 1 to each of them. So we get e to the 0 minus 1 is e to the negative 1, which is 0.368. E to the 1 minus 1 is e to the 0, which is 1. E to the 2 minus 1 is e to the 1, which is about 2.718. Right? We still have that horizontal asymptote at y equals 0. All we did was shift right by 1. So what we can see here that is this is a much higher number. Well, not much. This is slightly higher than 2. And it increases faster than it did when a was 2. So what we notice is the larger the value of the base, which is a, the faster f of x equals a to the x increases. So the higher the base, the faster it increases. So notice that when we first started talking about graphing exponential functions, I was very specific in saying that a had to be bigger than 1. Well, remember, a is always bigger than 0, so it's always positive. So now what happens if a is between 0 and 1? Well, that means it's a fraction or a decimal. And if it's a decimal, it is 0 point something, not 1 point something as a decimal, 0 point something. So it's bigger than 0, less than 1. Well, the domain stays the same. It is still all real numbers. The range stays the same. It's still 0 to infinity. The horizontal asymptote stays the same. We still have no x-intercepts. And the y-intercept is still 0, 1. What does change is that our graph has been essentially reflected about the x-axis. Because if you notice, we had negative 1, 1 over a. Well, that's still there. And 1 over a is all, or 1 and a is still there too, our ordered pairs. Negative 1, 1 over a, 0, 1, and 1 over a. But our graph is going the opposite direction. So what's happening now is instead of it increasing, it is now decreasing. And that's because it all comes down to what a is. When a is a fraction, then when we plug in 1, let's say our fraction is 1/3. 1/3 raised to the 1 is still 1/3. Right? So if I were to plug in 1/3, I had 1, let's say I had 1/3 to the 1 is still 1/3. 1/3 to the 0 is still 1. But what about 1/3 to the negative 1? Well, negative 1 says flip anything from the denominator to the numerator, anything that's in the numerator to the denominator, and make it all to the first power. So that becomes 3 over 1 raised to the first power, which is just 3. So now I have this point 1, 1/3. I have this point 0, 1, and I have this point, which is negative 1, 3. So it all comes down to reciprocals of fractions being larger than the fractions themselves. So we end up with a function that is always decreasing. So this is how it's different. It's decreasing if I have instead a fraction. So let's look at the graph. Let's look at our graph here of 1/2 to the x. Let's just do that one. We'll start there. Let's plug in some values for x and figure out what it equals. So we know a few points that should be on our graph. Let's see what they look like. So we've got x and 1/2 to the x. Okay, so let's start with the points that we know we need to plug in, which are -1, 0, and 1. And I'm going to leave a little space because I'm also going to try -2 in here. But let's start with -1. So -1 should be 1 over a. So if we plug that in, that would be 1 over 1/2. Well, let's see if that's the case. So 1/2 to the -1 is the same as 1 over 1/2, or the reciprocal of 1/2, which is 2. So -1, 2. So we have our point -1, 2. Let's plug in 0. We should get 1. Well, 1/2 to the 0 is 1. So we get 0, 1. It looks like it's doing what it's supposed to with the decreasing. Let's just make sure we plug in 1. I get 1/2 to the 1. A is 1/2, right? So this should be 1, comma, 1/2. Is it? Well, it absolutely is. 1, comma, 1/2. And then I said, I want to plug in another point like -2. And that's because I would like to have another point that shows how high it is up on the left side of our graph as we go closer to negative infinity. So if I plug in -2, I get 1/2 to the -2, which is the same as the reciprocal, which is 2 over 1 raised to the now the positive 2, which is just 4 over 1, or 4. So we have the point -2, 4. So it'd be up here. So does it look like it is decreasing? Absolutely. It's coming down, coming through and across, and getting closer and closer to 0 without ever actually touching it. So what else do we see? Well, we know that we've got our horizontal asymptote at 0. So we've got that coming for us. And other than that, it should have all the same information that we had from our graph when we had it, a being bigger than 1, except that now it's decreasing. And that's really about it when we start talking about some of that same information, which was the domain, which is still negative infinity to positive infinity. The range is still 0 to infinity. Now it still has a horizontal asymptote at y equals 0, and the y-intercept is still 0, 1, but now it is decreasing. So I mentioned that it looks like a reflection about the y-axis. Well, if that's the case, and we took 2 to the x, right? Let's try it and see. So it looks like 2 to the x reflected about the y-axis. Well, remember, if we're reflecting it around the y-axis, that's the same as multiplying the inside by a negative. Well, the inside here is just the x. Well, let's see if that's the case. So if that's the case, we would call this new function 2 to the negative x. Well, how are that and 1/2 to the x the same? How does 2 to the negative x equal 1/2 to the x? Well, if we think about it, that's the same as 2 to the -1 raised to the x, which is 1 over 2 raised to the x. They are, in fact, the very same equation. So whether it is a fraction raised to a positive x or it is a whole number raised to a negative x, we're going to have a decreasing function. So let's try some transformations on our decreasing functions. So if we take the same graph of 1/2 to the x, and now instead we decide we want to make it 1/2 to the x minus 1, we know that we're going to be shifting our graph to the right by 1. So every value of x that we just used is going to go up by 1. So what we had at -2 will now be at -1. What we had at -1 will be 0, 1, and 2. Let's just try this much. So if we plug in -1, I get 1/2 to the -1 minus 1 is a -2, which we just found out was 4. So I'll have -1, 1, 2, 3, 4. If I plug in a 0, I get 1/2 to the -1, which we know is 2. So we have 0, 2. At 1, I get 1/2 to the 0, which is going to be 1. And at 2, I get 1/2 to the 1, which is 1/2. And so, indeed, what we did is we took our graph from the last slide and we just went ahead and moved it to the right by 1. So it's still decreasing, still getting close and closer and closer to our horizontal asymptote at the x-axis, or y equals 0. So let's get that on there too. It is still decreasing, and our domain is still all real numbers, or -infinity to infinity. Our range is still 0 to infinity. It is still decreasing, right? We still have a horizontal asymptote at y equals 0. And now this time we went through 0, 2 for our y-intercept. The last transformation we're going to do is take our last graph, and now we're just simply going to multiply it all by 3. So let's make our same XY chart, right? And let's fill in some values here. Right? So we still have our -1. Let's see here, we'll go red maybe this time. Let's see here, x, and this would be, well, let's plug in our values from last time. So let's do our 1/2 to the x minus 1, and then let's just add in the shift after, or the stretch, sorry, after that. So let's see here. Trying to make sure I can get our lines in the right places. And let's extend this just a little here. Okay, I have a ruler that I'm using to help me draw these out for you guys. So now this time around, let's change it up to red. Let's do our 3 times our 1/2 to the x minus 1. So when we started before, we had -1, 0, 1, and 2. And our values were -1 was 1/2 to the -2 was 4, 0 was 2, 1 was 1, and 2 was 1/2. And where things get different now is we're going to multiply each of those values by 3. So maybe not all of them will end up on the graph, but we can try. And let's see what we get. 12, yeah, won't fit. Okay, it won't fit on the graph, so we won't have that one. But 3 times 2 is 6, we can fit that one on. So 0, we have 6. 3 times 1 is 3, so 1, we have 3. And 3 times 1/2 is 3/2, or 1/2. So 1, 2, 3, 1/2. So we're getting there. Right, now all of them will fit on our graph, but we can see certainly that we have now stretched our graph up, and it's now stretched out a lot more than what we had before. We still have our horizontal asymptote just like we did before, and now that's still at y equals 0. And notice that our domain and range still have not changed. They're both still the same, so we still have a domain That is negative infinity to infinity. We still have a range that is 0 to infinity. It is still decreasing. But now so it's a horizontal asymptote at y equals 0. And we are now have a y-intercept of 0, 6. So in the same ways that we transform functions when we were talking about other kinds of transformations with our toolkit functions, we now can do the same with our exponentials. So we're going to finish out this section with trying to solve a couple of exponential equations. And this is what we're going to be doing for our worksheet on Wednesday at the beginning of class together. So make sure you can figure out how to do all of these on your own as well. So make sure you're taking notes because you'll be allowed to use your notes for the worksheet. Okay? So what we're looking at here is I have 6 to the x is equal to 6 to the fifth. And so I gave you a reminder that said if a to the u equals a to the v, then u equals v. That is the definition of equality. In order for two things to be equal, every part of them has to be equal. So if these two have the same base, those bases are equal, then their exponents should also be equal. So in this case, x is simply equal to 5 because they have the same base. If we look at the second one, 5 to the x is equal to 5 to the negative 2. They have the same base. The bases are equal. Therefore, we will then set their exponents equal to each other, which means x is now negative 2. Where things get a little different is when we look at this third one. It says 2 to the negative x is equal to 16. Well, currently, they don't have the same base. So what we can do is make them into the same base. Well, I can make 16 a power of 2. This is 2 to the negative x. Well, 16 is 4 times 4. Well, 4 is 2 squared, and if I have 2 squared times 2 squared, that means 2 to the negative x is equal to 2 to the fourth, because we will add those exponents. And now that they have the same base, I can just set their exponents equal to one another. So if I set them equal to one another, then I've got negative x equals 4, which means x is just negative 4. That's one of our more complicated examples, but we're going to do another one, and that's this next one here. And that is that now we have 3 to the negative x, and it equals 81. And 81 we usually think of as 9 times 9. So 3 to the negative x is 3 squared times 3 squared, which is the same as 3 to the 2 plus 2, which is 4. So negative x here equals 4. So x is negative 4. So this is what we're looking at. These are our exponential equations. I know we have a section coming up next week that is also called exponential and logarithmic equations, but they're more complicated than these ones. So we're going to focus on these kinds for now. Here's some more. These ones are a little more challenging because neither side has the same base in this first one. So let's see if we can figure it out. We currently have 27 to the 4x is equal to 9 to the x plus 1. So what we need to do is figure out what base they both could have. Both 27 and 9 can be broken down to powers of 3. 27 is 3 cubed, and I can raise that then to the 4x, and 9 is 3 squared, and raise that to the x plus 1. So the way, remember, that exponents work is if I have a to the m raised to the n, that is a to the mn. If I had a to the m times a to the n, that one is a to the m plus n. That's what we saw in the last one. So now we get 3 to the 3 times 4 is 12. X is equal to 3 to the 2 times the quantity x plus 1. So 3 to the 12x equals 3 to the 2x plus 2. Well, they have the same base. Let's set those exponents equal. Subtract 2x from both sides. We get 10x, and it equals 2. Divide both sides by 10. X is 2 over 10, or 1 over 5. So let's try another one. This one might be a little easier. I have e to the 4x minus 1 is equal to e squared to the x. So we can make this e to the 4x minus 1 is just equal to the e to the 2x. And now, since they have the same bases, we can set their exponents equal. We get 4x minus 1 equals 2x. So subtract 2x over 2x minus 1 equals 0. Add the 1. 2x equals 1. X is equal to 1/2. And then the last one is sort of deceptive in that it can actually be pretty easily solved, but it doesn't look like it. So there's a couple of ways we can do this one. And the way I'm going to tell you to do this one is to think about it. Leave it as 1/5 raised to the x, and let's see if we can make this some sort of 1/5. Well, we know 25 is 5 squared. Well, guess what is also squared then? That's the same as 1 squared over 5 squared. And if that's the case, then I have 1 over 5 to the x is equal to 1 over 5 squared. And how can I just say that's 1 squared? Because 1 to any power is still 1. So 1 squared is just another way to write 1. So we just make the numerator and denominator have the same exponent, and we can move it to the outside. So that just means x is 2. The other way to do this one is you could say that's 5 to the negative 1 raised to the x, and that equals 1 over 5 squared. So we would have 5 to the negative x, which is equal to 5 to the negative 2. And negative x equals negative 2, which means x is equal to 2. You don't have to do it both ways. You don't even have to understand necessarily both ways. It's not a bad thing to know how to understand them both ways, but you need to be able to solve these kinds of exponential equations at least one of these ways. And our last example is, of course, a word problem. So how can I apply all of these exponential equations? Well, between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 15 cars per hour, which is a quarter of a car per minute on average. The following formula from statistics then can be used to determine the probability that a car will arrive within t minutes of 9 o'clock p.m. And that formula is f of t is equal to 1 minus e to the negative 0.25 t. So we wanted to determine the probability that a car will arrive within 5 minutes of 9 o'clock, so before 9:05 is over. So in that case, we have t equals 5, so we're just looking for f of 5. So all we're going to do is plug it in. 1 minus e to the negative 0.25 times 5. And when we plug that in, we find out that we get a decimal of 0.7135. And that is the same as 71.35%. So if we wanted to talk about probability, we often talk about it in terms of percentages. So 71.35% is something that we can relate to. There is a 71.35% chance that a car will arrive within 5 minutes of 9 o'clock. Part B says to determine the probability that a car will arrive within 30 minutes of 9 o'clock. Well, if we're averaging a quarter of a car per minute, that should be a pretty high probability considering we've had 30 minutes. So we should have on average had maybe 7 cars or more by then. But let's see, what is our probability? So we're 30 minutes in, so let's find f of 30, which would be 1 minus e to the negative 0.25 times 30. And not so shockingly, we find that we have 0 points. Our probability is 0.9994, or 99.94% that we have had at least one car come through within 30 minutes of 9 o'clock at this particular drive-through. So make sure you start working on homework 16 on Pearson, and we will do our worksheets at the beginning of class, right? The beginning of class together in groups on Wednesday. And it can be open note. So make sure you've taken notes from the video and bring them with you.